Good morning, everyone. Welcome to our first presentation through the Maker Faire Milwaukee. My name's Peter, and I'll be your host in the background here. We are super excited to be starting off this morning with Dr. Julia Klein. She's a structural mechanics and concept branch employee. She's an engineer. We like engineers here. She builds things in space. That's what her job is, to get ready to build things in space. So we're super excited to have her here this morning. Couple of things that just so you need to know. We're using Slido for polls and Q&A. So if you have a question, you can submit that. It's going to appear on the right-hand side of your screen, and you can submit a question to Dr. Klein. And throughout the presentation, we're going to be putting some polls out. So be ready to answer those questions. Without any further ado here, we're going to let Julia take over. And thank you for joining us today.
Awesome. Thanks, Peter. Hey, everybody. Good morning. Welcome to the first NASA Maker's Day presentation. As Peter said, my name is Dr. Julia Klein, and I work as an aerospace engineer at NASA's Langley Research Center. And so I'm going to talk to you a little bit about my career as an aerospace engineer, and then also talk a little bit about how we build things in space. So let's get to it. First, I want to help you get to know me, and then I'll take you on the journey of how I got to be where I am today. And at the end, I'll tell you a little bit about what I do at NASA. So hopefully that sounds good, and we'll go ahead and get started. Now, before I tell you about me, I want to know a little bit about you and who I'm talking to. So I know that we are going to have students watching this from across North America. And what I want to know about you is, what is your favorite subject to learn about? It doesn't have to be your favorite subject in school, but what do you like to learn more about? So if you go over to the poll, you can plug and type in your answers. You can submit multiple answers to the poll. I know there's a few of you watching with a couple of people on the screen, so you can type in your answers. And so we'll come back to the answers to that. But when most prisoners come and introduce themselves, they will do something like read out the things that are on their resume. And it goes something like this. My name is Dr. Julia Klein, and I have various degrees in space fields, astrophysics and aerospace engineering. I went to school for nearly 11 years after I graduated high school to get my education. And I worked as a postdoc for the Army, and then I got my dream job at NASA, and that's where I've been as an aerospace engineer ever since. And that's all well and good, and we'll talk a little bit more about how I got to where I am today. But what I thought would be most helpful for all of you was to get to know me, but back when I was in high school. Who was I, and what was I interested in back then? So, without further ado, I would like to introduce you to 15-year-old Julia Klein, who is actually more known as Julie to all of her friends and family. I was in 10th grade, and I was studying as part of the International Baccalaureate program, which is kind of like advanced placement classes. My favorite subjects were math and physics and history, and my least favorite subjects were gym and English, and I forgot to list on here biology. I am definitely not a biologist. I couldn't stomach the dissections that we had to do as part of biology class, and I feel like I tried my best to get out of those classes as best that I could. I got my first cell phone when I was in 10th grade because I was going to class across the city from where I live, and my parents wanted a way to be able to get a hold of me if they needed to. My cell phone was a like first generation Nokia cell phone. I think all it did was make phone calls and play the game Snake. Didn't do any of the other things that our cell phones do today. On let's see, on after school, I like to hang out with my friends, doing things like going to the mall and that sort of thing. On Friday nights, I could most likely be found hanging out with my family, and we did a weekly pizza night with all my aunts and uncles and cousins. I played the piano because my mom made me play the piano. And I was actually most likely to be found at the barn riding my horse whenever I could. And when I got my driver's license shortly after I turned 16, I was at the barn even more than I could be when I was 15. And I was also a Girl Guide junior leader, which is similar to the Girl Scout program. And lastly, you should know that I was probably about this age when I knew that I wanted to work for NASA one day. I remember sitting in my homeroom class, which was history, and my teacher, Mr. Levold, was reading the daily announcement. And on that particular day, the announcement was about a former Ainley student who is now working at NASA. And I thought to myself, well, one day, wouldn't it be cool if that were me? One day, could I be the former Ainley student who now worked for NASA? Before I tell you about how that one day became today, I need to give a shout out to my support system. My family and my friends have been there throughout my journey, encouraging me every step of the way and helping me realize my goals. My parents were especially encouraging to me and even took us on trips when my sisters and I were younger to go do sciencey things. We visited a meteor crater, we went to Kennedy Space Center, all sorts of places that helped feed my love of science and engineering. My advice is to find the people that support you, that are going to help you along the way, your family, your friends, and your teachers. And then my advice to those family, friends, and teachers of these budding scientists and engineers is to make sure that you're keeping encouraging your students and shepherding them towards their goal and supporting them at each step. The overall message of introducing you to myself at 15 years old is that I wasn't some super smart unicorn kid. I was regular. I did all the things that you do, and I just worked really hard to get to where I want to be. And there's not anything especially out of the ordinary about my experience or who I am. It's just that I feel like I worked hard and I took the opportunities that came to me to get where I am today. All right. So now that you know a little bit about me, you're probably curious, how did I end up becoming a NASA engineer? So I certainly don't feel like the path that I took after I graduated high school to go through college and get to NASA was linear. It wasn't a straight line, one to the other. I feel like there were a lot of times that I felt like I was moving in the opposite direction. I wasn't going forward. I thought I was going completely different than what would get me towards my NASA goal. But everything that I did all added up and gave me experience that was necessary to do the job that I do today. I started off by going to college and getting my bachelor's degree in astrophysics. I originally thought that I would be an engineer, and I applied to engineering school, but I didn't actually get in. There was an issue with my GPA when I applied, so I didn't get into engineering school at first. Astrophysics was actually my second choice. And I did consider switching back to engineering after year 1 and year 2, but I enjoyed studying about stars and galaxies in the universe, so I decided that I would stick it out and finish my astrophysics degree. But when I graduated, I decided I still felt like I should be an engineer. So I went to graduate school. I started my master's degree and went to the University of Texas at Arlington. And I got to study materials that are used for re-entry vehicles. So things like the space shuttle and the Apollo capsule, the Dragon, materials that come through the atmosphere that get very, very hot. So that was really exciting work. And I liked learning and I liked being a college student. So I was fairly easily convinced to stick around and continue to do my PhD. I made some changes and I was still studying materials, but this time for my PhD work, I studied materials that were used for helicopters. And I spent a lot of time in my laboratory breaking material specimens to understand how materials work when you pull on them, when you compress them, when you twist them. And this helped us understand real world applications because when we use these materials in vehicles and applications, we want to know how they're going to perform so that they don't break on us unexpectedly, right? After I graduated with my PhD, I moved from Texas to Maryland to live with my husband. He had been living in Maryland for a couple years at that point, so it was time for me to go and join him. I started doing what they call it postdoctoral research fellowship at the Army Research Laboratory in Aberdeen, Maryland. And I was still working on materials, so that's kind of the theme for all of this. But this time I was studying materials that are used for soldiers in their body armor and their helmets that protect them from enemy fire and those types of things. At some point, I probably figured that what I was working on was so far away from what NASA does. You know, NASA works on space and airplanes, that I would never be able to get a job for NASA. But I'm anything if not persistent. So I kept applying for NASA jobs online and hoping that one day something would stick. And it did. 2 years ago, actually next week, I became a NASA engineer. And I asked one of my bosses after I'd worked there for a little while, I sort of said, well, why did you hire me? What about me stuck out as the right person for this job? And he said that my resume, my career path to get to where I am had documented that I was a really good learner. I was really good at studying different subjects and learning them fairly quickly. I studied astrophysics for 4 years, and then I studied aerospace engineering. And within aerospace engineering, I studied a number of different materials topics. They were hiring me to do something that most people don't study in school. And so they needed people to work on this project that could learn very quickly and get up to speed. And the things that I had kind of looked at on my resume as being negatives had actually turned out to be really positive things in their eyes when they were looking at hiring me. So now that you know who I am and my career journey to become a NASA engineer, what do I actually get to do for NASA? What is the cool parts of my job? The first thing, of course, is that I get to think about space all day, every day, and that is pretty darn cool. The work that I do is under an emerging field called on-orbit servicing, assembly, and manufacturing. This is the here and now, the future of space. So breaking it down, on orbit means either in space or on the surface of another planetary body. Servicing is the repair or replace of equipment or things like that on satellites that are orbiting the Earth. So right now we put something up into space and we leave it there. But the goal is eventually to be able to go to these satellites, and we're actually doing it today, be able to go to these satellites and repair instruments that are broken, to be able to upgrade things like their computer systems or things like that. So if we were to think about maybe like the Hubble Space Telescope, we actually sent astronauts there several times over the Hubble's lifetime to repair and replace some of the Hubble's instruments. Now there's not a lot of the satellites that we have up there that we can actually send people to. So we're actually looking at doing robotics servicing, where we send robots and they are able to do the servicing operations for us. The Hubble has been orbiting the Earth and looking at the stars for over 30 years now. And we've done some upgrading of the Hubble's equipment, but a lot of what's on the Hubble is nearly 30 or so years old in technology. And if you think of some of the technology that has advanced in the last 30 years, I mean, your cell phone is one thing. When I was in 10th grade, about 20 years ago, there were, my cell phone was a brick and all it did was make calls. And now we carry around these little mini computers in our hands every day. For assembly, we're going to talk a lot about this because this is actually the area that I work in, but assembly is essentially building things in space. Manufacturing of materials and structures in space is also an area that this research area covers. Like we do on Earth, if we want to go to another planet or we want to go back to the moon and we want to have something like a city or a town or a settlement for our astronauts to live and work in, we are going to need to do some construction and we're going to need to manufacture the materials and structures needed to build those habitats and different things up there, because otherwise we have to take everything from Earth and launch it there, and that gets very expensive and time consuming. So we're looking at manufacturing techniques to be able to build structures on other planetary bodies. So in this picture, we're actually looking at 3D printing of a lunar shelter out of the lunar dust or regolith that's on the surface. So let's talk about building structures in space. So first, some famous spacecraft that are already up in orbit. We've talked a little bit about the Hubble already today, and we could talk about the International Space Station. How did these structures get into space? Well, they were launched. The Hubble Space Telescope went up into space in the back of a space shuttle, and the International Space Station was actually launched in pieces and assembled on orbit to make the larger structure. And the International Space Station is the size of a football field right now. We don't have a rocket that's large enough to launch something like that all intact. So the International Space Station is an example of in-space assembly work. There were pieces, they were launched, they were put together on orbit, and they made this larger structure. Each of those pieces had to fit inside of the spacecraft to get to space, and depending on the rocket that we use, we're limited in the size of the fairing that we can launch satellites into. So if you look at the James Webb Space Telescope, which is going to launch sometime this fall, this is a large space telescope with a nearly 7-meter diameter mirror. That yellow gold piece is the mirror. And they have had to do a lot of work to take the James Webb Space Telescope and be able to fold the mirror so that it's able to fit into a fairing that is about 5 meters in diameter. And so, what if we wanted to build bigger structures in space? This is always the goal. For telescopes, the bigger the mirror, the more light that we can collect. And the more light that we can collect, the more of space that we can actually see. So let's say instead of the 7-meter diameter mirror that we have on the James Webb Space Telescope, what if we wanted something that was 20 meters, 30 meters? Big, huge structures. How do we get that into space? Are we going to be able to fold it origami style and fit it into a rocket? Or maybe could we take up the pieces, build it on orbit, and use robots to do that? It's kind of like IKEA, but for space. And that's exactly what we're thinking of doing. And being able to build structures in space opens up a new design space for satellites and technology in space. We could build a big test bed platform. And that would mean that we could launch scientific instruments to space. And instead of having their own spacecraft associated with that scientific instrument, it could just be put onto the testbed platform and do its science without all of that extra complexity of designing its own spacecraft, which means that we can get experiments into space much faster and much cheaper. We could build large solar collectors that could harness the power of the sun to provide power to the Earth and to other planetary bodies. And we could even build space nuclear propulsion vehicles, which are about the same size or bigger than the International Space Station, that can be used to transport humans to Mars. All of this is enabled if we're able to build and assemble structures in space. My team is actually gearing up to build a 20-meter structure in our lab over the next few years to demonstrate that we can use autonomous robots to assemble structures to build confidence in the technology before we take it to orbit. Now, speaking of humans, does anyone know where NASA is sending the next man and first woman this decade? Any guesses? There's a poll in the chat if you want to put in your reply. Good. It looks like everyone is up on their NASA news. We are going back to the moon. And going back to the moon is going to help us for our eventual destination of Mars. Everything that we're doing as part of the Artemis program is helping us prepare to send humans to Mars. When humans arrive at the Martian planet, they will need to have a base set up with shelter, power, communication, food, and water, all of the things to sustain life and exploration for an extended period of time. We're going to use a permanent lunar base to actually help us prepare to go to Mars. Now, shelter, power, communication, all of this sounds like things that we have here on Earth, in our towns and our cities, big structures, buildings. We're going to need to do some construction work and build on planetary bodies as well, just like I've been talking about doing for telescopes and platforms in space, and what we do to build bridges and buildings on Earth. Now, think of a construction site on Earth. Hopefully you've probably seen one. They're all over. What do you normally see as part of the equipment on a construction site? It's probably one of the tallest things out there. And you can drop in the poll in the chat your guesses on what you might be seeing at this construction site. Great answers. Now, we need everything that you guessed, but for those of you that guessed a crane, you are 100% right. Since we're going to be doing a lot of building work and construction on the moon and Mars, it's probably a good idea that we have a crane with us to do some of the heavy lifting. Our team at NASA thought the exact same thing. And about 10 years ago, they started working on what we call the Lightweight Surface Manipulation System, or LSMS. It's a crane that we can use on the moon and on Mars. It's lightweight, and it folds up very easily so it can package into a rocket fairing. And it can work in a gravity environment like we have on the moon and on Mars. And it can be made in different sizes so that it's able to pick up different sizes of payloads, from small scientific instruments all the way to habitat modules, like is shown here in the picture. A crane can help us in unloading a lunar lander and moving things onto the surface, to building structures, and to even doing things like moving rocks on the surface and doing grading and those types of construction activities as well. When we think about the lunar or Martian surface construction, a lot of it needs to be done before astronauts arrive. so that the habitat and the settlement is ready for the astronauts when they get there. Robots like the LSMS will need to be able to operate autonomously with minimal human intervention to accomplish these tasks, which means we don't have a human there controlling every move. We have the robot doing things and then radioing back if it needs help from an operator. There isn't so much of an issue with communication delay between the Earth and the Moon, but Mars is really far away. And depending on where the two planets are, Earth and Mars, in their orbits with respect to one another, there is somewhere between a 3-minute to a 22-minute one-way communication delay. So think if you're playing your video game at home and you move your joystick, you want to walk forward, and you have to wait 22 minutes to see what happens, and then 22 minutes back to be able to make your next move. It's a long time to wait. And so similarly, when we are operating robots on the surface of other planets, we need to be able to operate, faster than that. It helps with safety and just getting jobs done in a timely manner. And so we're going to use this technology, and we're actually going to practice it on the moon, because the moon is our test bed for Mars. So if you have interest in robotics, autonomous robots, computer science, all of this, there is a ton of work to do in the lunar construction field. Wow. That's all I had on our agenda for today to talk about. So we're nearing the end of this discussion, and there's just a little bit more that I want to leave you with before we go. Over my career, I've learned a lot of lessons that I think are really helpful to share. First, the path to success, as you saw from mine, doesn't always seem like a straight line. So if you say yes to good opportunities and you always learn from situations that you're in, you will do well and you'll gain experience necessary for the job that you want to do. Sometimes failure can be the best teacher. You're gonna fail, and it's gonna happen, and it's okay. You'll need to persevere and keep going. You gotta pick yourself up and keep pushing towards your goal. My PhD advisor also impressed upon me that happy people do good work. He used to tell me that all the time. So it's important that you enjoy what you do. You want to be able to get up every morning and enjoy your job and enjoy the work that you get to do and feel fulfilled. You want to balance work and your home life. And if you're able to do these things, you're going to do well in whatever field you're in. So much of my journey came from saying yes to good opportunities, even if I didn't really see at the time how it was going to fit with my overall goal. I kept trying to learn, and I tried to be as open as I could to change. Other factors in your life are going to change your path. For instance, I had no plans originally to move to Maryland, but when my husband had a job there, that was where it took us. And then my job has brought us to Virginia, where we live now. Find your people that are going to help you along the way and support you. Find someone that does the job that you think you want to do, and ask them all of the questions that you have. There's no dumb questions, especially when it comes to figuring out what you want to do with your life. Ask them what they love about their job, and ask them what they don't love about their job, because sometimes that's really more of an important question, because it helps you decide what you might want to do. And lastly, focus on the skills that you need to do the job that you want to do. You don't need a PhD to do a job necessarily, so if you don't need one, you don't have to go and get one. Do a little bit of research and understand what kind of training and schooling that you need to do in order to do your dream job. Thank you so much for having me this morning. It's been my pleasure to spend some time with y'all. And for fun, here's a picture of me and my husband and our 2 dogs hanging out on Mars earlier this year. This was part of a photo booth fun activity as part of the Mars 2020 promo materials when we launched the Perseverance rover and when it landed on Mars. So if you want, you can go to the website there and you can make your own photo on Mars. So I think we have some time, so I'm happy to answer any questions that anyone has. Thanks.
Julia, thank you. Wonderful. Really appreciate your time and your insight. I learned so much already. It filled my head with all sorts of things, more to write about. Um, to everybody who is joining us here, you can um, use the Slido Q&A. Oh, it's over on the right side of your screen, and you can submit questions. And we actually have our first question coming in, so I'm going to make it live.
Okay.
And I'm going to send that over to you. And the question is from Isabel. What type of technology do you use for testing your materials?
Yeah, that's a great question. Thanks, Isabel. So for material testing, a lot of what we used were what we call test stands in the laboratory. So these are pieces of equipment that are designed to apply a load to a specimen. So for instance, if we wanted to pull on a specimen, we grab onto it, and then the machine actually pulls on it at a specified rate, and we can pull on it really fast, we can pull on it really slow, depending on what we want to learn about the material. And then we use a lot of really cool technology to understand how the material performs when it is pulled on. So for instance, how much you pull on a material, the load that you apply, and the amount that that material stretches and then also contracts is important information for us to know when we design structures to use these materials. So we use a technique now called digital image correlation, which is where we actually use cameras to take pictures of the material as it's deforming, and then computer software analyzes those pictures and tracks features on the surface to measure the displacement. And so we can understand sort of that relationship between the load applied, the force, and the displacement. So that's one of the main technologies we use, but there's lots of other technologies depending on what you're trying to learn about the material.
Wow. Wow. Very, very cool. And again, over on the right side of your screen is the Slido Q&A, and we've got time. What a unique opportunity to ask Julia some questions here. While we're waiting for the questions to come in, I have a question. What kinds of subjects would you tell students to, they're kind of in the start of their thinking about maybe they want to work for NASA. What should they study? What kind of classes should they take?
Yeah, that's a really good question. So one thing that I learned when I started working for NASA is that you don't have to be a scientist and engineer to work for NASA. NASA employs a lot of people from many different industries. So if STEM fields are not your thing, there's still a place at NASA for you. We have finance, lawyers, all of those people. But
Hello.
if you're interested in the science and engineering side of NASA, we also employ a lot of different
Yes.
scientists,
Thank you.
biologists,
You too.
physicists, chemists, all sorts of people in those fields, different types of engineers. A lot of the ones that I work with are either aerospace or mechanical engineers, but I mean, we have electrical engineers and civil engineers as well. NASA works with a lot of, we work with astronauts. So we have medical doctors and nurses that work with our astronauts and study how space affects humans. So there's those fields as well. And then, I work with a lot of computer scientists and those that do a lot of computer programming. I think that's probably a skill that everyone has to have nowadays as an engineer in a lot of the fields is being able to write computer code and be able to do that.
Wow. The diversity of careers at NASA are huge.
Yes.
I know that we've gotten a chance to work with educators quite a bit
Yes.
to help teach about what NASA is doing, but we've met many scientists, engineers, a doctor.
Yeah.
Uh, so very cool. We have another question. This is about English and language arts. So I'm going to promote that up here. It show up on your screen here. You mentioned that English was not your favorite subject. But did you read and write, science fiction? Did you watch movies? Did you have a kind of a, it says here, a visual feel for space?
Yes. That's a really good point. So I should probably qualify my English, my dislike of the subject of English. So I love to read. I love to read as a student, books, chapter books, whatever. I usually had a book with me to read. Studying the English side and understanding Shakespeare and those types of things wasn't exactly my jam. But I love to read and I love to kind of watch movies. Big Star Wars fan. Star Trek. My dad was a huge Star Trek fan, so we used to watch that with him. And I loved movies like Apollo 13 and Space Cowboys and all of those. Anything that was about space was kind of cool. I could be expected to do that. I will say I was kind of rudely awoken when I got to graduate school. I thought that I would be able to go through life not needing to be able to write an essay or something like that. But a lot of what I do in my job is actually writing papers and writing scientific communication. So I've had to work on my skills writing papers and writing essays and that sort of thing, because it's a critical element to my job. So having those skills is important in being able to effectively communicate what you're doing.
Sorry, can I ask you a question? Because I'm using web browser, was not able to type chatting.
Sure, Tracy, please.
Thank you, thank you. So my question is, Julia, excellent presentation, it's great. So my question for you is, you mentioned a little bit about 3D printing. Can you be a little bit specifically how 3D printing do the job?
Yeah, sure. So there's a number of different technologies, associated with 3D printing. There's, we have laboratory scale, 3D printers that basically melt plastic and can build structures and that sort of thing. But there's other ways to 3D print, including sintering of materials, so heating it up with a laser and sort of melting it down to create a structure and that sort of thing. So there's a number of different NASA entities as well as commercial companies that are looking at how we can use the technology of 3D printing in space. So one of them, with the lunar dirt and regolith, is looking at how we could potentially heat that lunar regolith with a laser beam or something like that to kind of fuse it together and melt it and create a structure that has more strength than just sand and dirt. But there's I believe they have a 3D printer on the ISS, and they used it to make a wrench. A few weeks ago, I was reading about NASA. Actually, they needed a wrench that they didn't have on the International Space Station, and so they designed what they needed on Earth, and they emailed the file. They sent it to the ISS, and they put it into their printer, and they were able to print that and use it on the space station. So, in terms of being able to quickly make something, tools that we need and those types of things on another planet or in space is kind of a cool technology to have. So I think we're going to see a lot of that happening in space.
Wow, that's super interesting. Isabel had another question here about the microcontrollers. That's what we do here. We work with microcontrollers here at Gearbox. But maybe more expansively, just the computers and what kind of, you mentioned coding and computer languages. What kind of computers and microcontrollers do you use to control your construction robots, let's say?
Definitely, definitely. So I'm gonna start with, I am not the expert in this, but we actually in the laboratory use a lot of kind of off-the-shelf things that we can get to do a lot of our research. So things like Arduinos and Raspberry Pis and stuff like that. There's a lot of that in our laboratories that we use. We use that to proof out what we're trying to do. And then as we get more sophisticated in terms of technologies, we're looking at some commercially available serial robotic arms. When we want to get more expensive, we're starting to assemble these large structures. We'll start to look at some of those types of technologies, but for a lot of the research, it's kind of these simple things that we hardwire up ourselves.
Very cool. We love the Arduino, so
Yes.
we have a lot of fun with it.
Yeah.
I had one question. It's not about the technology or the coding, but do you work in a team? I mean, do you work with others? What's the kind of the work environment at NASA? I'm very curious about that. We meet you as an individual.
Yes, and that's a very good point. And yes, I work on a huge team. For all the projects that I work on, it is not just me. It is me and a lot of other people. I work on a couple different projects. For one of them, I'm the project lead. So I kind of organize what's happening, and I report up to management and tell them what we're up to and what we've been doing. On other projects, I'm a researcher. I'm part of the team. I have a project lead that I report to and I work with. But a lot of what we do in OSAM is very heavily interdisciplinary and heavily interrelated. So my background is materials and structures, but we're trying to get autonomous robots to build these structures. So we work very closely with a team of autonomy engineers who are, working on the robots that are going to build these structures. And so there's probably at least 20 or 30 people on each of the teams that I work with. So being able to work on a team and do your part and get along with others is a really, really important component of my job.
Wow, super. That's a huge team.
Yes.
The big team. We have time for one more question. So if you want, we've got one more opportunity to toss one into the Q&A and get it out there. And while we're waiting for that, Julia, we want to thank you, and we want to thank the Office of STEM Engagement at NASA as well. Been very helpful in meeting you, finding you in the sea of NASA people. Phenomenal. We really appreciate your time and your enthusiasm and sharing. Really is huge. We will make sure we get that link out to everybody who has stopped by and seen your presentation. And while we're doing that, maybe we've got one more question coming in here. Do you have any final pieces of advice for our audience, people watching this?
Just a big thank you for tuning in today, and just keep doing what you love. If you love science and technology, engineering and math, keep pushing. There's a place for you in this field, no matter who you are, and just find what you're passionate about.
Super. And I think we had a shy audience member. They didn't finish
No worries.
Well, on behalf of the Maker Faire Milwaukee, thank you very much on behalf of Gearbox. And it looks like we have one question, and what I'll do is I can take it off of mute here. Betsy's is asking a question. I think she wants to ask it verbally.
Sure.
Go ahead, Betsy. I've sent you the unmute.
I'm just thrilled to meet you, and I wanted to thank you personally, but the Slido seems to have jammed on my computer. So I look forward to, will you be attached to other ventures so you can come out and talk to some of us? how would you describe the first way you got tinkering with things? That's a big question for some of us older people who are not quite sure how to encourage younger ones to direct their efforts.
Yeah, so I feel like the biggest tinkerer in my life is my dad. He, when I was growing up, was always working on cars, was always doing something in his garage, whether it was fixing an old car or woodworking or home renovations or those types of things. And so he had 3 daughters, and we were his helpers. So if he needed help in the garage or something like that, we were out there with him, helping do things. So I sort of learned to appreciate, hands-on work and that sort of thing through my dad. So I think exposure, is getting kids in situations where they can tinker and they can, you know, play with things and understand how they work. I also remember when I was younger, the science experiments that we got to do as part of class. Some of those are the most memorable things. Like, it's been 25 years since I was in elementary school, but the things that I remember the most are the projects that I got to work on. So in elementary school, we built a burglar alarm in one of my classes. And so we used electrical circuits to wire up a shoebox house. And there we used, a little simple light, and we had to wire that so that the light would go on when the door opened, an alarm would go off when our window opened, and that sort of thing. We did an egg drop challenge. We had to design a holder for an egg that we, dropped off a ladder to see if, it would protect that. We built bridges out of popsicle sticks. In one of my physics classes, we built a roller coaster. All of those cool projects just gave me such a hands-on understanding of that. And I was, very fortunate. My dad was usually right there helping me put together my project and teaching me along the way what I needed to, do to make my project successful. And so those projects helped. I never did any like official science fair projects or anything like that, but I mean, I think those types of activities are good too. And nowadays, like I said, computer programming and being able to do things like Arduinos and Raspberry Pis and write code and applications and things like that are just so huge. So I think any exposure to those types of things is really crucial and beneficial.
Thank you.
Super question, Betsy.
Yeah.
Appreciate that. That is all our time. And again, thank you, Julia. We really appreciate it. Dr. Klein.
Thank you.
We're super excited to have you present today. And we definitely will stay in touch. And we will be posting a copy of this recording through our social media channels. So you can follow Maker Faire Milwaukee and Gearbox Labs on social media, and we'll be posting this link probably in the next couple of weeks. But we want to thank all of you for attending and participating with us.
Thank you.
Thank you.
Thank you.
Have a great
Thank you
rest
so
of your
much.
day.
It's excellent.